Welcome to the classes on coordination compound. It is class number 27, higher secondary second year. So before starting the class, let me tell the coordination compound, which is in a very important chapter in higher secondary second year. The chapter is a bit big, but for your knowledge, I am telling that if you just follow each and every class, I'll separate the class into three parts. I'll complete the three-part class within three lectures, and if you follow each and every lectures, you can answer each and every questions, and each and every year there are a lot of questions being asked from this coordination compound in competitive exam point of view, and this is a very important and interesting class. And from very beginning, if you can understand and try to follow me, you can very easily understand the class, and you will find much interested in dealing with the topic of coordination compound. And this coordination compound has a profound application in inorganic chemistry and also in biology, biochemistry, and lots of applications are there. Hence, it has a tremendous utilization in day-to-day life time. And before starting the class, let me tell that I have already started physics in hand by me, and you please check out the classes, and these classes are only meant for the entrance exam, any type of entrance exam and CUT. So kindly just follow physics in hand by me. So before starting the coordination compound, let me first explain one thing, that why these compounds are called coordination compounds and what are the coordination compounds. First of all, you should have a clear-cut, crystal clear knowledge upon this fact. Then we will proceed bit by bit with a lot of information, and this chapter is a quite informative chapter. So we see So let me first tell that when solutions of two or more salts are allowed to combine in a solution, a compound or complex is formed, and which are as follows. I am taking two examples. One is potassium sulfate, aluminum sulfate plus 24 molecules of water, and you will get K2SO4, Al2SO4 whole thing dot 24 molecule of water, and that is FeCN2 plus 4KCl equal to K4 FeCN6. We have seen that two salts when added, we are getting two different compounds. Now let me differentiate what are the types of this compound. That is potash alum, and this is a complex. Now let me distinguish what is a salt and what is a answer is a salt and answer is a complex. Let me start with this fact. So it is actually a double salt, and it is complex. So the main fact lying in this reaction is that the double salts and complex in the reactant part, we see the complex figures are there. Compounds are in complex type, but one is double salt, other is complex compound. Now, what is the difference between double salt and complex compound? Here, compound A, the result of A gives you a double salt, means if you dissolve this salt in the solution, you will get ion of potassium, ion of aluminium and sulfate. All types of ion will appear in the solution, and if you test it, qualitative analysis, you will get the response of the presence of the ions of potassium, sulfate, aluminium individually. So this is called double salt. But here in the second case, what we have got K4 FeCl holding 6, and we have termed it as a complex. But if you now dissolve it in the solution, you will find this. like this. Now the fact is that there is iron Fe, either it is 2 positive or 3 positive, we'll later on see it, and there is potassium ion. We are getting the test of ion, the solution when this react product is dissolved in water, we will get the test of potassium ion only, but we will not get any response of Cn negative or Fe2 positive or Fe3 positive in the solution. This is the fact. This is the complex where when a complex is formed and if you dissolve this complex in solution, you will find some of the ions and you may not find the ions, you will find the result as this. You will not get the response of Fe ion, 2 positive or 3 positive ion on Cn negative ion in the solution. If these things happens, then this compound is called complex. Now we will be dealing with the coordination compounds of the type this, not double salt type. Now to come to the main point of the coordination compound, let me take one more example. With the help of this example, I will explicitly explain the function or the way or the properties of the complex compound and why we call this compound a complex compound. It will be very clear to you. Now let us come to the point how a complex compound appears and what will be its structure. From the very simple example, it will be very clear to you. If you can understand this example with clear understanding, you can understand the whole chapter coordination compound very easily. If you have any confusion, you can't proceed further with crystal clear ideas. So minutely follow. Just I have written a compound in this way: CCO3 cobalt, CCO3 6 ammonia, and I have treated with its silver nitrate, and I have told you the result is thrice AgCl. It is PPT out, precipitated. We will get 3 mole of AgCl. Now just ammonia, I have taken here 5 ammonia. Now AgCl is treated. We got twice AgCl. I have taken 4 ammonia, 4 nitrate, CCl3 4NO3, and I have got 1. And when it is CCl3 3NO3, I have got no AgCl precipitation. Now the fact is that you may think that the same CCO3CNH3, and there is a bit difference in the ammonia 6, 4, 5 and 3, but we are getting the mole of AgCl formation when it is made to react to silver nitrate AgCl. Means here in the structure there should be some chlorine as chloride, ionizable chloride. If from here there are some ionizable chlorides are there, then that chloride reacts with AgCl positive, will get AgCl PPT, and that chloride number of chloride ion should be 3 to get 3 AgCl. Am I right? Means in this compound, I don't know what is structure. In this compound there is 3 Cl chloride ion, and that's why it has given 3 AgCl. And here there is 2 Cl3, 2 Cl negative in this compound. In this compound there is 2 Cl negative ions, chloride ions, and hence here twice AgCl. And here only 1 Cl negative means chloride ion. It gives 1 mole of AgCl. And here there is no Cl chloride ions and had no AgCl PPT. Now the fact is that you can tell or ask a question: how can you tell that here there is C3 chloride as ions, here 2 chloride as ions, here 1 chloride as ions, here no chloride as ion? How can I assume this? Where from the knowledge come? Now the fact is that there is some difference in the structure. Now I am just telling you that somewhere there are some chlorine which are ionizable, and there are some chloride which are not ionizable, non-ionizables. There are some chlorides that becomes Cl negative, and there are some chlorine which doesn't become ions. There are some chlorine has become chloride, and there are some chlorine which doesn't dissociate into ions, and there are no chloride dissociating into ions. How can you understand this? Now, simple for the first case, just if you write the structure in this way, CONH3 whole thing C and Cl3 is third bracket, out of third bracket C Cl3, then this outside bracket Cl3 will just when dissolves in water, it breaks up as ions at 3Cl negative, and that ion when made to react with AgCl3, it gives you thrice AgCl, and this total in the reaction mixture product will get 3 ions. This is 1 and this is 1, 3 and 1, 4 ions in the solution. If you forget about these things, we will get 3 AgCl. So also in this case, you will just write here for case number 1, this is the fact. For case number 2, I am just explaining only 2 cases. This will be CO Cl3, and here ammonia is 5. Just will take 1 chlorine inside the third bracket and 2 chlorine outside. So you see here 2 and 3 is 6. Here total 6. Am I right? We are getting this. Sorry, CO is 1 CO, NHC, NH3 5 is 5, and chlorine has 3 chlorine, 2 chlorine out. Earlier 3 chlorine out. Here 2 chlorine out, 1 chlorine inside. Means that outside 2 chlorine will become now twice Cl negative, and that twice Cl negative will react with AgCl, will give you twice AgCl. Likewise this, and here no chlorine outside, all chlorine inside. So from this type, a lot of question often asked from this point. From this, we can conclude the structure of this and this as like this and other ways. Means complex coordination compounds, there are some different structure of the compound, and due to the difference in the structure, the reactions product are different. So now, how can you assume that the structure is like this, structure is like this, structure is like that, structure is like that? So that was dictated by a famous chemist whose name is Werner. So Werner theory, again this is very important to understand. This is the backbone of organic chemistry. So let us explain what Werner tells. If you understand this one, so my first example of thrice AgCl, twice AgCl, 1 AgCl, no AgCl will be crystal clear to you all. So minutely follow. This is not tough, very simple, and patiently you follow my class, and I assure you, you can understand and explain each and every conceptual question from this, and also able to answer the questions in entrance also in your class exam. Just I have written the first one. Minutely follow. There are two types of the in the just let me take one example. Say it is complex. So the first example I have shown you here, this is complex. So now, if you draw the structure, I will draw the structure, you will find there are two types of balances of the central metal. Here central metal is cobalt. That cobalt central metal will exhibit two types of balances in all types of a complex compound. One valence is called primary valence and other valence is called secondary valence. Number one. I will explain what is primary valency, what is secondary valency. Number 2, the primary valencies are satisfied by oxidation state. The primary valencies are correspond to oxidation states of the metal and are ionizable and represented by dotted lines, and these valencies are satisfied by anions. Very important things you mind that when we will represent the structure of this Werner's theory, applying Werner's theory, we will get some valencies which are called primary valency and some valencies which are called secondary valencies. Primary valencies are generally represented by dotted line. And number 2, what this primary valency? These valencies are correspond to the oxidation state. This cobalt has oxidation state maybe 2, maybe 3. If the oxidation is 3, there will be primary valency 2, 3. If the oxidation state, I will explain how to find out the oxidation state. If its oxidation is 2, then its primary valency will be 2. So primary valency always corresponds to the oxidation state of the central metal. Now, this primary valency, whatever the oxidation state, that number will be its primary valency, and that valencies are designated by dotted line, and that valencies will be ionized. If chlorides are primary valency, then all the chlorides will be ionized. There will be 3Cl negative. These are ionizable. And now these valencies are satisfied by anion or neutral molecules. Am I right? So if these are primary valencies, then these primary valencies are satisfied by anions only. Here chlorine is Cl negative. That primary valency means negative, means anion, chloride ion, and that primary valency will be satisfied by the number of anions. What will be the number of primary valency? That primary valency will be equivalent to the number of anions. If its primary valency is 3, there will be 3 chloride, or there will be 3 SO4 2 negative. Negative ion will satisfy the number of primary valency. This is first point. Second point, third point is that so second type of valencies are called secondary valencies. When we will draw this structure, we will find some secondary valencies, and this secondary valency is secondary valencies are nothing but the number of coordination number of the central metal. Now again I will tell coordination number, how to find out coordination number. At maximum metal, central metal has coordination number 2, 4 and 6. Mind that these are the fixed coordination. Each and every central metal has the fixed coordination number, and what will be its coordination number? That will be the number of the secondary valency. The number of secondary valency is equivalent to the coordination number of the central metal ion, metal atom or metal ion, and these secondary valencies are represented in structure by a line, thick line, and these thick line ligands, maybe termed as ligands, are non-ionizable. They do not undergo ionized, they are never ionized in solution. So we have understood two types of valencies. Now let me take the first example. So at the very beginning, I took this example CCl, cobalt CCl36 ammonia, and I told you there are 3 chloride ions in the solution. Now you can understand very easily. I am explaining now what is primary valency. Now coordination number of this cobalt is 6. It will be clear a bit later. I will explain what will be its coordination number. What is coordination number? Coordination number is 6. So secondary valency is nothing but the coordination number of the central metal, atom or ion. The central metal is cobalt, its coordination number is 6. So thick line 1, 2, 3, 4, 5, 6. There are secondary valencies, 6 number of secondary valencies with ammonia ligand. And now talk about the primary valency. Here 1, 2, 3, the dotted line bonds are nothing but primary valency. So these 3 are primary valency. These 3 are ionizable in the solution 3 chloride negative, AgCl3 thrice AgCl it will give. So this is something about the primary valency and secondary valency and their representation and their ionizing ability in the solution, whether ionizable or not. Now next one, every metal has fixed coordination number 246. I told you every metal has fixed coordination number, and anion play a dual role of satisfying primary or secondary valencies of the central metal ion. One thing probably I have forgotten, secondary valencies are satisfied by anion. You please adapt. Secondary valencies are satisfied by anion, so also neutral ligand. Anion and neutral ligand. Example we will get later on. Ammonia is an example of neutral ligand. I will explain a bit later. So primary valencies are satisfied by anion only, but secondary valencies are satisfied by anion and also sometimes by neutral ligand. That's why anion has a dual rule. It can satisfy primary valency, so also it has the ability to satisfy secondary valency. That's why I have written every metal has fixed coordination number, and anion play a dual role of satisfying both either primary or secondary valencies of central metal, atom or ion. Again, very important, very often a lots of type of questions, short questions are very often asked from this theory. You please keep it in your mind. Each and every point should be clear to you, otherwise you will find difficult to answer the question. The secondary valencies are arranged in space. They arranged in space. There is partial arrangement of what valencies? Secondary valencies, and around the central metal, and give the geometrical shape of the complex. The complex has octahedral, tetrahedral, you will get later on. It has some shape, and this shape arises due to the spatial arrangement of atoms or molecules. And these atoms and molecules are nothing but attached with the secondary valence. Hence, the shape or the geometrical shapes of the complex give rise due to the secondary valencies arrangement in the space. But the primary valencies are non-directional. They do not have any direction. They are non-directional. They do not contribute any towards the shape of a complex. This is all about the valuable Werner's theory. Now, let me take one example and come to the focal point. This is an example of traditional compound, a complex compound. This is metal. These are ligand. I'll explain what is ligand. I am coming bit by bit. This is coordination number. I told you a bit earlier. I will tell later on. This is coordination number and it is fixed. So actually, what is coordination number? Coordination number means inside the third bracket, the metal is surrounded by some ligand, maybe ammonia, maybe chloride, maybe sulfate, maybe water, maybe anything. All this ligand surrounding the central metal is nothing but coordination number. You just calculate the number of ligand attached to the central metal, and that number will give rise to the coordination number. If the number is 6, coordination number is 3. If it is 5 and there is chlorine, 5 and 1 6, there is 6 number of the atoms or ions, anions or ligands attached around surrounding the cobalt, and all these things which are surrounding the central metals are nothing but coordination number. Now the whole this part mind that inside the third bracket whatever is present is called coordination pair, and all these are non-ionizable. They do not get detached as ions and ligand. Cobalt some positive and 6 ammonia positive, negative or neutral, nothing. They never backs up like this, hence they are non-ionizable, and this non-ionizable part of the complex coordination compound is called coordination pair. So I have got coordination number, ligand, metal, coordination pair. Am I right? Instantly a question comes in your mind, how the bond, what types of bond appears in the formation of metal ligand in a coordination complex. Metal is surrounded by ligand, and how these are bonds are taking place. What types of bond are taking place? Number one, these things is a bit complicated, just I am giving you the insight complexities of the structures. There are some electrostatic force or electricity bonds, that is attractions of the electron pairs between metal and ligand. This is high type of, very strong type of force. Then second type of the force is the covalent bond, and this is sharing of the electron pair between metal and ligand. And third type is coordination covalent bond. There is the donation of electron pair by the ligand to metal. Ligand will give the electron pair chiefly to the metal, one-sided. So it is coordination covalent bond. Generally, three types of the interaction take place during the bonding mechanism of the metal ligand. This is very important, and you must know the concept regarding ligand. What is ligand? Very often I use the term, very often I have already used the term ligand. And what is ligand? Ligands are anions. Ligands are anions or neutral molecules. Neutral molecules, water, ammonia, etc., CO, all are neutral. I will explain when it's classification. I will explain with example. Anions are the neutral metals that form coordinate bond with the metal atom or ion. The ligand forms a coordinate bond with metal atom or ion. That coordinate bond means the ligand or anion or the neutral atom, neutral molecule will give lone pair of electron to the metal, will donate lone pair of electron to the metal. And if this anions or neutral molecules has the ability to donate lone pair of electron and forms a bond with the metal in this way, is called ligand. So ligands are nothing but the species, anions or neutral molecules which have the ability to donate lone pair of electron to the metal to form a coordinate bond. So these are ligands. This is a very crucial point. Very often you will get confused and very often you can't keep it in your mind very easily, and I will show you diagrammatically, and I hope you can very easily understand the types of the ligand. Type of ligands here I will explain on the basis of three factors. I have just prepared it for your clear understanding. The type of ligand you will get nowhere. Just try to understand on the basis of charge, on the basis of number of donating site, on the basis of bonding nature. Now, on the basis of charge means minority follow the types of ligand on the basis of charge. I have classified into three categories. One is negative ligand, positive ligand, neutral ligand. If the charge is negative, negative ligand. OH negative, Cl negative, NO2 negative, Cn negative, and lots. All negative ligands are of this type, basing upon the charge are negative ligands. Now, second type is positive ligand. NO2 plus, NO plus, etc. NH2, NH3 plus, hydrogenium ion. Anyway, neutral, ammonia, water, CO, NO, etc. These are neutral, no charge are there. So, on the basis of the charge, there are three types of ligand: negative, positive, neutral. Now come to the very striking point: number of donating site. Ligand may donate lone pair of electron from different sites. One ligand may donate from one atom, from carbon, from nitrogen, from oxygen, from chloride. Other type of ligands are there. They may donate the electron to the metal from one side, from two sides of the molecule, from three sides of the molecule, from four sides of the molecule, from six sides of the molecule, depending upon the donating of electron pair from number of the atom of the molecule is now the basis, number of donating site. So now number of donating sites, you see the donating site, it is donating from one site. So if donating site is one, that is from one atom, if it donates the lone pair of electron to the metal and makes bond, then it is called monodentate. Cl, monodentate. From one atom, it is attaching with the metal by donating one lone pair to the vacant d orbital of the metal. Now, if it at the molecule I am considering NH2, CH2, CH2, NH2, ethylene diamine. Ethylene diamine. Ethylene diamine En, symbolically En. So you see here in this molecule, it is donating the lone pair of electron to the metal from two sides, one from this end, other from this end. From these two sides, the link to the metal is taking place through two sides, and it is bidentate. Now, polydentate, say CH2, CH2, NH2, NH2, I have written here only NN, and CH2 CO negative. Actually, this is CH3COOH acetic acid. When it is bonded, one hydrogen is reduced. And if remove this one, this. When acetic acid, one hydrogen is removed, it is called acetate. So this is acetate, CH3COOH bonded CH2COOH is removed, CO negative. So here it is attached to the metal through this, through this four side. It is called ethylene tetraacetate. Ethylene diamine tetraacetate. In short, it is called, very important, ITA. Very often question comes in exam, ITA. So these are the different three types of the ligand depending upon the number of sites through which it is making a coordinate covalent bond with the metal. If through one side it is monodentate, if through two side it is bidentate, if it is three side, four side, more than two, it is polydentate. I have here taken the example of polydentate is ITA. Now depending upon bonding, here depending upon the bonding nature, bonding type, means sometimes in the same molecule it is making a bond with the metal with O, other time with N of the same molecule. Means bonding nature is different. Say NO2 is attached with the metal. If it is ligand, NO2 is ligand through O. And other time, same NO2 is attaching with the metal through N. So the site of bonding is changed. That is type of ligands are called ambidentate. Another is SCN, CNS. Once it is S, other is through C. This type of ligands where bonding changes with the metal of the same molecule, different time, different bonding, is called ambidentate. Number two is chelating. Now what is chelating? Means CH2, NH2, CH2, NH2. I have shown you here ethylene diamine. It is chelating. It will link with the metal in this way. So it makes a ring. When a ligand makes a ring during a bond with the metal, then such type of the ligand is called chelating ligand. And next one is pi acid. It is very, very important, tremendously important in entrance point of view. I will take some time on this one, pi acid. And one of the very important ligand is CO. CO is pi acid ligand, and just I am explaining a bit. You can, I think you can understand. Here it is a type of ligand which is called pi acid ligand. Means the ligand CO at the very first it donates electron pair through carbon C to the backhand d orbital of the metal. It is sigma type, direct to the metal. And another type, field metal d orbital, donates electron back bonding to the backhand pi star of the ligand, anti-bonding orbital of the CO. So once the ligand is donating electron as earlier characteristics of ligand with the metal with the sigma, and other type field metal orbital is now exchanging or returning or back bonding with the backhand pi star orbital of C. Such type of the ligand are called pi acid ligand. And third type ligand is called bridging ligand, and this bridging ligand very often OH Cl and NH are used in bridging. Just I will tell you one example. You can very easily understand this type of bridging ligand. Uh, Here you see your ligand, sorry, this is cobalt, uh, is being attached CO tetraaqua, 4 CO tetraaqua, and the bridge OH. Bonding type is that type. If such things happens with this OH, may also with Cl, may also with NH. These type of bondings are ligands are called bridging ligands. So in a nutshell, on charge 3 type: negative, positive, neutral. Number of bonding site: monodentate, bidentate, and polydentate. Number of bonding sites: abidentate, chelating, and pi acids and bridging ligand. Crystal clear to you, nothing to learn by heart, just to keep it in your mind, and lifelong you can answer the type of ligand abidentate. Any type of question you can answer, so you just keep it in your mind. Now I am giving you some preliminary concept before giving you the rule of naming the coordination compound. Very important, very often asked in entrance exam, CUET exam you will get. And before that I will make you prepare how to write the names. I will give you some tips how to find out oxidation state of metal. How can you find out oxidation state of metal? Say I am taking one example, K4 Fe CN6, this. Now if I want to tell you what is the oxidation state of iron, simple. The potassium, it is plus 1, charge is +1, 4 is 4. I don't know this, say X. And cyanide, all are negative, Cn negative, one charge. There is only one charge with Cn. So 6 1 ja -6. And in the above there is no positive, no negative, means you give it here 0. You will find 6 - 4 equal to -2. Here iron is oxidation state is 2. The tricky thing here, very often you will find difficulty in finding, say a structure is written, you have given a structure, it has name is given, and you are asked to write this structure. You will find it difficult to tell. Please minutely follow this point. It is very interesting and very clumsy and very confusing. Very often you will not able to find the write the structure. You see, your structure say in a rough way. I am telling. The name is given chloroamine. By amine alphabetically amine. You may write it earlier. Aminochloro. Chloroamine aqua cobalt 2 chloride means the oxidation state of cobalt is given 2. Am I right? So here oxidation of cobalt is 2. And ammonia is the neutral ligand. It has no charge. Charge is 0. Chlorine is negative. Only one negative charge is there. -1. Now it is chloride. I will not talk about this, because here chloride may be 2, here chloride may be 3, here chloride may be single. I don't know what will be its number here. 2, 3, 4, I don't know. So I will not write this chlorine in the calculation. I will first calculate what will be its charge. Let me first find out its charge. Depending upon its charge, I will satisfy this charge according to Werner's rule by negative ion. If charge is 2, I will give 2 negative. If charge is 3, I will give 3 negative. If charge is 1, I will give 1 negative. So this primary valency will be balanced by the number of the charge of the complex ion. So let me calculate the charge. I sorry, it is cobalt 3, it is cobalt 3. So here you write 3, and here there is x, you give x. I will find the number of charge, either it is positive or negative, my calculation will give the result. So here we have got x equal to 2 and this is 2 plus. Means simply if you dissolve it in water, it will ionize as chlorine negative, it will go out as negative and that part will be positive. Answer should be positive, that's why you have got 2 positive. Since x equal to 2 positive, there will be 2 negative charge anion to satisfy. So your structure will be CO NH3 Cl water Cl2. Am I clear? Likewise, say you are given it is not given in this way, the name is given potassium hexa cyanoferrate 2. The oxidation state is given ferrate. Why it is ferrate or iron? When will you write ferrate, when will you write iron, that depends upon some rule, I will tell it a bit later. So since it is given in this way, roughly I have written KFeCN6 like this. So here oxidation state of iron is 2 and cyanide is minus negative minus 1, 6 1 the minus 6. I will not assume chlorine as earlier, and here this is x is equal to this. So here answer is minus 4 equal to x. That is the value of x has become minus 4. So I am to give plus 4k. So your structure will be K for FeCN6. This is all about the way to find the coordination number, to find the oxidation state, to find the charge on the complex metal. Last but not the least, En. For entrance point of view, this is very important. Effective atomic number. What is effective atomic number? It is now atomic number of metal minus oxidation state plus say you are asked to find out the effective atomic number of this compound. So what is the atomic number of the iron? It is 26, it is known to you. What is the oxidation state? 6 minus 4, you find out oxidation state of this one. This is 4, this is plus x, this is minus 6 equal to 0, therefore x equal to 2. That is oxidation state of this is 2 equal to minus 2 plus coordination number is 6. Am I right? Coordination number is 6. 6 into 2 equal to 2. This is equal to 24 plus 12 equal to 36. The effective atomic number of this complex is 36. You can tell the what is the applicability of this. It is very important fact, because sometimes you will be given some numbers of the complex and will be asked which one is more stable, which one is less stable. It is one of the factor with the help of which we will calculate that if we find this number correspond to the number of noble gas, helium, neon, argon, krypton, radon, xenon, if these numbers correspond the noble gas configuration, then this complex is a stable one. And another factor of stability of the coordination complex compound is that if there is ligand which forms a ring, chelating ligand is there, the stability will increase. Hope you have understood the class, followed the class minutely. Today I have come to end of this class, and please don't forget to check out physics in hand. I have just started the higher secondary physics for entrance point of view. I have uploaded 2 class. You please check out by me physics in hand, and in the next class I will start the nomenclature of the coordination compound along with the bonding, very important for entrance point of view. Thanks for watching the class.